Yeah, welcome to Complex Analysis Module, Lecture 15. Today we will see what is Cauchy Residue Theorem. In part 14, we have seen how to find the residue for the different type of singularities. Means in case of removable singular point, pole and essential singular point. So let's see first what is the statement of Cauchy Residue Theorem. So let C be a simple smooth closed curve and let Fz be analytic inside and on C, except at a finite number of isolated singularities. Means this theorem is only for isolated singular points. I told you there are two types of singular point, isolated and non-isolated. In your syllabus, isolated singular point and isolated singular point again can be classified in three singular points: removable singular point, pole singular point, and essential singular point. Pole singular point. So if you have these types of similarity, then you can apply Cauchy residue theorem. So let C be a simple, smooth closed curve and Fz be analytic inside and on C, except at finite number of isolated singularities Z1, Z2, and Zn lying inside C, then integration along closed curve C. Means you have a curve. Suppose this is a simple, smooth closed curve. Inside this function is not defined at Z1, Z2, Zn. Z1, Z2, Zn are actually your singular points. So singular points are points where our function is not defined, as z is not defined. So if fz is defined everywhere, then the line integral fz is dz is always zero according to Cauchy integral theorem. But if it is not defined at some point, then we can apply. It has some type of singularity, then this integration is equal to 2 pi I sum of all residue 1 to n d1I. D1 is representing residue. I is representing corresponding to first singular point, second singular point, and nth singular point. Or you can write it is equal to 2 pi I sum of all residues. Residues we always calculate for a singular point. So this is the only statement of this theorem. I'm not going in the proof of this theorem. So let's solve some questions. It is given. So evaluate these integrals, evaluate the integrals. So this theorem is more useful in comparison to Cauchy integral formula. And this is more general form in compared to Cauchy integral formula. In Cauchy integral formula, you need 1 upon z minus z naught term in the denominator, but here not necessary. So you want first question is 1 over e to the power z minus 1 dz, and the curve is given mod z equal to 1. Let's see the solution. If we compare this with fz dz, so you can tell me what is fz here. Fz is actually 1 over e to the power z minus 1, singular points where function is not defined. So here denominator is 0, that will be the singular point. So z e to the power z equal to 1. We know that 1 is e to the power z. We can compare z equal to 0 is a singular point. Z equal to 0 is a singular point. Or you can think there are many singular points actually. If you write in the general form, one can be written as it cos 0 plus I sine 0. Actually, I have to write like this, not like this. Then you will get better idea. It is equal to cos 0 plus I sine 0. Now write it general value. So cos 2r pi plus I sine 2r pi. Okay. So it can be written as e to the power 2r pi I. Now if you compare z equal to 2r pi I, and r is starting from 0, 1 to 3 and so on. So you can see that if you draw the curve mod z equal to 1, the first singular point z equal to 0 is in the center and it is inside the circle. What about second singular point? That is 2 pi. 2 pi I is on the y-axis and minus 2 pi I on the negative y-axis. So these points are outside to the curve. So these are the similarities, but not lying inside the given curve. Therefore, we cannot include these singular points. So only singular point we have to deal, that is z equal to 0. So only singular point is z equal to 0. Okay. So let's evaluate the integral now. So you have to find the residue for it. Let's see the residue now. So integration f z dz is equal to 2 pi I sum of all residue. I told you sum of all residue. So here it will be e to the power z minus 1 dz equal to 2 pi I b1. Actually, you have only one residue here, one singular point. So only you have to find one residue. What is b1 here? b1 is a residue of fz at z equal to 0. So it will be the, can you tell me how to find it? Yeah, it will be the coefficient of 1 upon z minus 0 in Lorentz series expansion of fz. What is fz? E to the power z minus 1. So can you expand it? Sorry. Can you expand it? Yes, we can expand it using Lorentz series. So b1 is actually one, if you take the expansion of e to the power z, coefficient of 1 upon z in the expansion of 1 upon e to the power z minus 1. So you try 1 upon e to the power z minus 1. It is actually z plus z square plus z cube factorial 2 factorial 3 and so on, because 1 is cancelled out. Now you can take z as a common. Z you can take common here. So 1 upon z, it will be 1 plus z by factorial 2 plus z square by factorial 3 and power is minus 1. So it will be 1 minus z by 2 minus z cube by factorial 3, neglecting higher order term. So 1 upon z minus 1 upon 2. You can see that minus 1 upon 2 minus z square by z by factorial 3. So can you tell me the coefficient of 1 upon z? That is actually 1 here. So b1 is 1 here. So as you put b1 is equal to 1, your answer is 2 pi I. Your answer is 2 pi I. Okay. Let's see the next example. This is the 8th example. I'm going to solve this problem now. Yeah, this is the I think the not correct question. It should required. I have to check it. It is I think minus 1 is there, or plus minus 2 or minus 1. You have to see. So you can see that it can be plus 1 also, no problem. Then its picture is wrong actually. Minus 1 and minus 2 both are lying here, and it's lying inside the circle which radius is 3, and minus 1 and minus 2 both are simple poles. So you know the singularity to find. So b1 is the first, that is singularity at z equal to minus 1 actually, and it is minus 2. And you know the formula. It is a residue of fz at z equal to minus 1. In the case of simple pole, z equal to minus 1 and minus 2 are simple pole. You can see my previous lectures. So it will be limit z tending to minus 1, z plus 1 into fz, and you can find the value of first b1, second z equal to minus 1. Similarly, you can find the residue for second point, and then you can add both these singularities and you can multiply with 2 pi I. That will give you the complete answer. Similarly, in the third problem, it is cot z mod z equal to 2. So in this case, you can see that cot z, if you compare fz dz, can you tell me what is fz is? Fz is cos z upon sin z. Can you tell me where function is not defined, where sin z is 0? Sin z is 0 at sin n pi. So z equal to n pi, and is a plus minus 0 plus minus 1 and so on. So z equal to 0 plus pi minus pi and so on. But if you see the circle is mod z equal to 2. If you draw mod z equal to 2 circle, radius is 2. So therefore 0 is lying inside the circle, but pi and minus pi are outside. So other singular points are not lying here. So only singular point is z equal to 0. And we know that z equal to 0 is a simple pole, because sin z has z equal to 0 as a simple 0. Therefore, its reciprocal function which will have simple pole. You can see my previous lectures. So your b1 will be actually it is simple pole, and it can be written as phi z upon psi z. Then I told you this is phi z naught upon psi dash z naught, where z naught is the point. It is point is 0, so phi upon psi dash 0. Here phi z is actually your cosine z, and psi z is equal to sine z. This question I have already solved. Phi 0 is cos 0. Psi dash derivative of sine z is cos 0, so it is 1. So b1 is 1. Then you apply in the integration formula. Your integration will be 2 pi I into b1. So the integration is going to be 2 pi I. If only residue is asked, the value is 1. If integration is asked, integration is 2 pi I. Okay. So if you are taking mod z, actually you need 4. Then you can see that there lie more than one singular point. It is actually 4 in the question. It should be 4 actually. Then if it is 4, take two cases. Mod z equal to 2 and then mod z equal to 4. If mod z equal to 4, my dear students, then pi and minus pi both will lie inside. In the case of mod z equal to 4, pi and minus pi both lie, and even 0 will also lie. So in that case, you have to find 3 residue. First residue of fz at z equal to 0, that is 1. This is a residue of fz at z equal to pi. It is also 1. And can you tell me how this is also 1? Because I told you this problem, all the residue are 1 in the case of sine z. You can see my previous lecture. So the next question is, this is an important question and asked in many exams. Integration e to the power z minus 1 upon z, z minus 1, z minus iota square dz, and this is your fz. Here I am taking two cases actually. In the first case, I am taking mod z equal to 1 by 2, and in the second case, I am taking mod z equal to 2. So what are the singular point where the function is not defined? 0, 1, and I. Now we have to classify the singularity, nature of the singularity. Then only you can find the residue. So check the, I told you in the case of removable singular point, if z equal to z naught is a removable singular point, then I told you limit z tending to z naught fz exists. But function is not defined. So check here, limit z tending to 0. What is fz? E to the power z minus 1 upon z, z minus 1, z minus I whole square. And we know that due to this expression, this limit is existing. Because we know that limit x tending to 0, e to the power x minus 1 upon x equal to 1. So this is one value, and if I z equal to 0 in the denominator, it is existing, its value is 1. So z equal to 0 is a removable singular point. Where other point, if you check the limit z tending to 1, it is upon infinity. If you check z equal to 1, suppose you check limit z tending to 1, z minus 1, z minus I whole square. This limit is tending to infinity. So not existing, therefore z equal to 1 is not removable singular point. It is a simple pole, and z equal to I is at degree 2, it's a pole of order 2. So in the, you have to find all the 3 residue. In the first part, mod c equal to mod z equal to 1 by 2. Therefore, only singularity is lying, that is z equal to 0, because 1 and I both are outside. In this case, you have to find only one residue, b1, that is residue of fz at z equal to 0. And this value is 0 because in the case of removable singular point, your residue is 0. Your residue is 0. So integration is going to be 0. In the second part, when mod z equal to 2, all the 3 singularities are lying inside the circle, only 0, iota, and 1. So you have to find all the 3 residue, b11, b12, b13. b11 is a residue of fz at z equal to 0. It is 0 due to a removable singular point. Then at z equal to 1, you have to apply the formula for simple pole, limit z tending to 1, z minus z naught fz. And you can see that this is e minus 1 upon minus 2i. Then b13, pole of order 2. So you have to apply the formula for pole of mth order, 1 upon factorial 2 minus 1. Actually, it is wrong. M minus 1, m is 2 here. Limit z tending to z naught, that is I, d by dz, z minus z naught whole square of z. And if you calculate, you will get this value. The integration is 2 pi I, sum of all residue. Sum of all residue. So you can multiply 2 pi I and then add all the residue. Okay. So this is your question. Now I'm going to solve a most important question that asked sometime in 10 marks question. Very important question, most important. So integration, I'm going to solve it completely. 1 upon z to the power 4 plus 1 dz. And the curve is mod z minus 1 equal to 1. Now, if you compare it fz dz, can you tell me what is fz here? Fz is 1 upon z to the power 4 plus 1. So singular points are the collection of points where function is not defined. Z to the power 4 plus 1 equal to 0. So z to the power 4 is minus 1. We have to find the fourth root of minus 1. This can be written as implies that not like this. Z equal to minus 1 to the power 1 by 4. And we know that minus 1 can be written as cos pi plus I sin pi. You know that. Now use the general value, that will be cos 2r pi plus I sin 2r pi plus pi to the power minus 1 by 4. Okay. Now use the de Moivre theorem. So cos 2r pi plus pi by 4. This is plus 1 by 4. Plus 1 by 4. Plus I sin 2r pi plus 2r pi plus pi by 4. Now, what is the value of r? R equal to 0, 1, 2, 3 here, because we will four roots only. R or k, some people take k also. Now, as you put r equal to 0, you will get the first root. Suppose this is zr, z equal to 0, r equal to 0. Then you are getting cos pi plus I sin pi, that is 1 plus I by root 2. Z1 means r equal to 1, cos 3 pi by 4 plus I sin 3 pi by 4. This is minus 1 plus I by root 2. Similarly, Z2 means third, that will be 1 minus I by root 2, and 1 that is you are getting minus 1 minus I root 2, and Z3 you are getting 1 minus I by root 2. And we can see it's a complex conjugate also, 1 minus I and its complex conjugate minus 1 minus I. So there are four roots, Z0, Z1, Z2, Z3. You will get four roots obviously because the power is 4 here. Okay, now we will check which of the singular points are lying inside the given curve. So the given curve is mod z minus 1 equal to 1. If you simplify it, it can be written as x plus iy minus 1 equal to 1. Or you can write x minus 1 plus I equal to 1. Or it can be written as x minus 1 under root whole square plus y square equal to 1 square. Or you can write, 1 x minus 1 whole square plus y square equal to 1 square. The circle which center is 1 comma 0 and radius is 1. So this is a look like this circle actually in the first and fourth quadrant. And the roots are the 1 plus I by root 2, minus 1 plus I by root 2, Z2 is 1 minus I by root 2, and Z3 was minus 1 minus I by root 2. It is lying in the third quadrant because both are negative. Here x is positive, y is negative, so it can be lying. Okay, x is negative, so it cannot possible because here x is positive. So only you have to check Z0 and Z2. Z0 is 1 by root 2, 1 by root 2 lying here also, and Z1 minus I. This is your Z1 and this is your Z3. Both are lying inside. So only you have to calculate the residue about these 2 points, B11 plus B12. Means B11 will be the residue at Z1 and B12 is the residue at Z0, and it is your Z2. Okay. So you have to find the residue at these 2 points only. So let's calculate the residue here. So for that we can see that our Fz is actually equal to 1 upon z to the power 4 plus 1, and it can be written as phi z upon psi z. And these all are simple poles. How can you claim that these are simple poles? Because z to the power 4 plus 1 is written as in this form now. Z minus Z0, Z minus Z1, Z minus Z2, and Z minus Z3. We know that if any quadratic or any equation have the root n roots, then suppose this is equation, it can be written as 1 upon x minus alpha 1, x minus alpha 2. If it has n root, then x minus alpha n. And if you break the partial fraction, you will get the linear factor. So all are the simple poles. So you have to find the singularity using the formula of simple form. So B11 is residue at z equal to z naught, phi z naught upon psi z naught. So phi z naught is a phi z is here 1. And what about psi z? Psi z is z to the power 4 plus 1, and its derivative is going to be 4z cube. Okay. At z naught, it will be 1 upon 4 z naught cube. Multiply z naught in the numerator and denominator, z naught upon 4 z naught to the power 4. And we know that z to the power 4 plus 1 is 0. And its roots are z0, z1, z2, z3. So all the roots will satisfy it. It means z0 to the power 4 equal to minus 1. So the first singularity is, first value is, residue is minus z0 by 4. And similarly, if you find z equal to z2, it is minus z2 by 4 also. Are you taking z2? Yeah, z2, 1 minus I. I think he used the second another notations. I am taking, you can see which is you are assuming z0, z1, z2, z3. I think he has taken z3 like this, and I have taken z3 this and z2 this. It depends which what notation you want to use. That's not problem. Only you have to find the value of residue. Then you add the residue. Adding is very easy. Z0 by 4, Z2 or Z3 by 4, whichever you are assuming here, and add the value, put the value of Z0 and Z2 or Z3, you will get this integration. This is a very important integration. So this is the ending of the Cauchy residue theorem. In the next lecture, we will see some application of Cauchy integral theorem. Okay, thank you.